Okay, welcome to Unit 2 on filtering and note set 6 in our digital audio signal processing course. This is the last note set in this unit, although we will continue using the results from this unit, especially the all-pass filters and the comb filters that we'll learn about here. So a couple places or a few places you can read about this. So this is a nice introduction. I'm going to follow that perspective to introduce these. Proacus and Montelakis talk about a more generalized version of comb filters, and we'll hit that at the end of this note set. And in the DAFX book, chapter 2, there is some coverage of application of these ideas to audio. And that's what we're interested in here. So starting from the way Orphanidis introduces these ideas in his general DSP book, that's what I'm going to follow here. And why are we looking at these? Well, because comb filters, not necessarily the simplest FIR one, but comb filters in general are used a lot in audio signal processing. In particular, later on, we'll see that audio effects like delay or echo and reverb and flanging and chorusing, these all use the structure that is known as a comb filter. They use them in different ways. So a very important building block. So let's start with this simplest view, just to sneak up on the idea of what is a comb filter. So if we take the output is equal to the input plus some delayed version of the input with some scaling factor. And I say that magnitude of A is less than or equal to 1. In this setting, technically it can be larger than that. There's no, technical reason why it can't be for this FIR version. But for audio, it's unusual to set A bigger than 1. That would be the case where the echo sounds louder than the original. Might be an interesting effect, but generally not something that we would want. Okay, so let's take a look at this particular filter. To do that, we're going to look at all the different ways we have to look at this. Well, except for state variable. We won't look at the state space view of this, but we'll take a look at all the things that we use to understand how a particular filter or system works. Block diagram, transfer function, pole zero plot, frequency response, and impulse response. So here is one of my famous diagrams, and you can see I've got ovals, which are in time domain, rectangles, which are in frequency domain. And then I think of the block diagram. See, it's kind of rounded off rectangle. So it's got parts of both of those. Kind of lies in between. You can think about it as a time representation. You can think about it as a Z domain representation. So we start here with the given difference equation. And then we can say, well, the output consists of the input plus a delay with a weighting factor. So we immediately get this block diagram. The output is a sum of the input. There's the sum. There's the delay, and there's the weighting factor. So we can immediately write out that block diagram. So you kind of see how it's time domain and Z domain, and we could sometimes replace this by X of Z and Y of Z. So it's just a fundamental way of thinking about the system. Now we can also go from here and just take the Z transform, and we get the transfer function in that form. And we see that, yes, this is an FIR filter. And we could then, to find the pole zero diagram, it's more convenient to convert into the Z form. So we would multiply top and bottom of this by Z to the D. That should be a D. It looks sort of like a P. And then we get this form. Then we look at numerator and denominator. and we find the zeros of those, and that will give us the poles and zeros. So we see that we have D poles at the origin. So I'm showing those there with a bunch of X's that make this asterisk, and then labeling how many there are. And then we also get D zeros, and we show those here, and they're going to be at a radius of the dth root of A. So A is a real number, could be positive or negative. If you take the dth root of that, you'll get some number, which we'll call rho. We'll take the real positive value of that, since that's giving us a distance or a magnitude. And then the angles of these zeros are such that if we take rho times e to the j, whatever one of these angles is, it gives the complex polar form representation of those zeros. And if we plug that into here for z, raise it to the dth power, it will give us a negative a, which will be a zero of that. So that's how we think through that. We'll go into that in a little bit more detail in some other examples in just a little bit. Now we can go from here to here, just replacing z by e to the j omega. And so now we get the frequency response. And to see what that looks like, well, we would expand that out into a cosine plus a j sine term using Euler. That puts this quantity here in rectangular form. And then we can do our square root of the sum of the square of the real part plus the square of the imaginary part to find the magnitude. And so what you would get is something that looks like that. And you can see that there is a cosine dependence in there, but there's a square root also. And so that's why we get this kind of up and down that is controlled by that cosine. But it doesn't look like a cosine by itself because of the square roots and everything else that's in there. But that's the basic nature. And what we see, we can tie this back to our pole zero diagram, right? We have a bunch of zeros. They're not on the unit circle, but they are pulling things down. And then in between, if you remember at some point when I talked about this, maybe in the review notes, I said, think about the pole zero diagram being built on an air hockey table. So the zeros are tacking the tent surface down. But in between the zeros, the air hockey table is blowing the fabric up. So that's what's creating these peaks here. So those peaks are going to be at very specific positions here. And so they will be between the locations of the zeros. So we'll have one here at 0. And then we'll have one. So this distance is pi over d, and this distance is 2 pi over d. So we'll have a little bump up here, which turns out to be here at 2 pi over d, and then 4 pi and 6 pi and so forth. So equally spaced. We can see that here. We can see that here. That's the idea. And then from here, we can inverse z transform back. The 1 goes directly to a delta of n. That's right off the z transform table. And then using the time shift property and the linearity property allows us to transform that back to a delayed delta function. So here's our impulse response. So that makes sense. We're kind of adding a delayed version of the input. So the input goes in and immediately comes out, right, straight through. And then a delayed and attenuated version of it comes out D samples later. So that's the classic hello, hello, coming back as an echo, but just a single echo. Okay, so that's our simplest comb filter. Why do we call this a comb filter? Well, look at its frequency response. It looks like the teeth of a comb. And so that was historically why these things were called comb filters. Okay, so looking at this plot just a little more carefully and analyzing the equation that we have for it, we can take a look at why this ends up looking like a comb, or at least some of the details of it. If we analyze this, we can see that the largest value that it will take is 1 plus a, and the smallest value that it will take is 1 minus a. So remember, that is only assuming that the a is limited between plus and minus 1 in that case. And we also see the locations of the peak. So even integer multiples of pi d, or perhaps a better way to say that is integer multiples of 2 pi over d. And if we want to write out equations for where the peaks are, we can say there's our integer k. I didn't state that here, but I think it's pretty clear from the context. So k is an integer. So integer multiples of 2 pi over d. Now, we always want to think about how these filters tie back to the physical real-world frequencies. So if we convert this in radians per sample into hertz, that would be taking and multiplying that by fs over 2 pi, because fs corresponds to 2 pi. So the 2 pi's cancel, and we get kfs over d. So that's where those will be located. Now, notice here I'm showing this from 0 out to 2 pi. It would also go in the other direction. Remember, it's 2 pi periodic, so we're really interested in the minus pi to pi region. The nulls are going to be in between those, so those would be at positions denoted like that. Again, the spacing is 2 pi, but they're offset by pi. And if we convert that into hertz, we get something that looks like that. So, so now we know exactly where those peaks and nulls lie. It's not super big important thing, but it helps to understand how these filters work. And if we let a be equal to 1, then these nulls are going to go down to be all the way down to 0. So they would be actual zeros on the unit circle. That's why we would have those. Okay, so that was the simplest comb filter. Now let's extend this idea. We're going to keep it as an FIR filter, but instead of just adding one delay, we're going to add more echoes. So we'll put one. So the first echo happens D samples later, and then D samples after that. So 2D relative to where the original signal was. We'll have another one, but that's weighted by another application of A. So here it gets multiplied by A, and here it gets multiplied again by A. So we're thinking about, we're calling these echoes, and we're thinking about how this might occur. It's a sound that's bouncing perhaps between two walls of a room. Each time it hits a wall, it gets attenuated by the factor A. And so that's why we get A, and then A times A, and then A times A times A. And it takes D samples to go from one wall to the next wall. So that's the idea here. Now we can just look at this, and with our understanding of how transfer functions work, we could think about taking the Z transform of this and working a little harder to find this. But we've done that, so we know that this will correspond to a transfer function that looks like this. The A and the minus D give us that structure, A squared and the minus 2D, and the A cubed and the minus 3D. So that's how we get that. Now, I should say, look at this. We see, yes, it is an FIR filter. We can see that from its structure of its difference equation. We can see that from the structure of its transfer function. But to analyze this, it will be helpful to convert this into a slightly different form where it's not so obvious that it's an FIR. And we'll see why that's helpful in just a little bit. So if we use the geometric series, now there's two forms for that. If you Google that and look it up, there's one form that says you've got a series of numbers that are added together that are related by successive powers, and we have that here. But for the finite geometric series, there's finitely many terms, and that will always be applicable. And we get something that looks like this here. In just a little while, we'll apply the geometric series for the case where this goes on and on and on infinitely. And in that case, there's only certain conditions where you can apply that nice formula for the geometric series. But if we apply the finite geometric series, we can rewrite this clearly FIR transfer function in this form. And we see, aha, there is a denominator here that tells us this looks like an IIR filter. But it isn't. It isn't. We know it's an FIR filter. Now, this is one of those subtle things. I had mentioned this earlier, maybe in the review or somewhere else, that there was a subtle distinction between the concept of recursive filters and IIR filters. Most people just kind of use those terms interchangeably, but here's an illustration. This is actually a recursive form of this FIR filter. This is the non-recursive form of it, and this is the recursive form of it. Now, you can't always write an FIR in a recursive form, but sometimes you can, and this is one of those cases. So I just wanted to point that out. Bottom line is both of these end up being the same transfer function for the same filter, and it's an FIR filter. Okay, but why we want to do this is that it will help us understand the structure of the poles and zeros of this. So let's take a look at this. We're going to take the result that we just had, which is in inverse Z form, and we're going to multiply top and bottom by the most negative power of Z, and that gets us into a Z form of the transfer function, and that's the form we want to look at to get poles and zeros, at least when we're doing it by hand, not so much by the Z-plane command. So now we look and see what are the roots of this polynomial and what are the roots of that polynomial. That'll give us the zeros and poles respectively. So if we look at the numerator, there's just this z to the 4d minus a to the 4th. So if we set that equal to 0, that is equivalent to that equation there. So any z that satisfies that. And so we can see that that's going to be like the 4th roots. We're going to have to take the 4dth root of that thing. And then the denominator, there will be roots of this, and that's captured here, but there are also 3d roots due to that term. So that's the z equal to 0 term. Okay, so looking at that, we can say, well, here's our zeros. They're going to be numbers that satisfy that. And so it's going to be a row, which is the 1dth root of A, and then the complex, or the angles of the complex part of this in polar form ends up being 2 pi k over 4d. So you can see when you start raising that to the 4d, that's going to cancel, and you get all these integer multiples of 2 pi. So that will line those all up on the real axis so that they can end up canceling the A4. So that's how we get that structure. And then the poles, well, there will be 3D poles at the origin. That comes from this, and then similar kind of thing here. So those will be at angles of 2 pi k over d. See, this was over 4d because of this, and this is just over d because of that. So that's what we have. Now notice that the poles and zeros that we found here are all at the same radius, and rho is going to be a positive number, positive real number in this formulation. So, but here's the thing. These zeros are at this radius, and they're going around every 2 pi over 4d. These poles here, which we shouldn't really have because this is an FIR filter. We should have these, but we shouldn't have those. Turns out that these fall at some of the same places that those zeros do, and they end up canceling. And so all the poles that this formulation seems to show that are not at the origin end up canceling with zeros. And so we end up getting only the 3D poles at the origin, and then we get 3D zeros, same structure as we had up here, except now K is not a multiple of 4. That's where those poles would have canceled those. And so that's the idea. And then we have our 3D poles at the origin. So that's our pole 0 structure. And so let's just take a look at this for D equal to 8 and A equal to 0.5. Using this form, we'll see what we end up getting here. And so now I'm going to put this into Z plane. So I'm going to use D is equal to 8 will give me D minus 1 is equal to 7. And 4D minus 1 is 31. So that's how I figured out how many zeros to put in there to make this polynomial here. And so now if I run that, I get something that looks like that. Now that does show all the poles and zeros, and it shows them where they cancel. So now if I were to put into this the form that we started with, so I could also put in this FIR, explicit FIR, I could put this in as the numerator of the Z-plane command and then put a 1 in for the denominator. And it would show me a slightly different view of this. It wouldn't show the poles and zeros that cancel. It would just show all of these zeros here that don't cancel. It would still show the 24 poles at the origin. The only reason I'm doing it this way is just so that you can see the structure. And then remember, there's nothing here, so that gives a little wider space for something to pop up. These are constraining down pretty well, only a little bit of pop-up in between. And we see that structure down here in the frequency response plot, which I just did with freq Z. Okay, in fact, I did it the same way. I put those things into freq Z. So now let's look at this. We're going from minus pi to pi. And we see, at omega equal to 0, so that's along this axis here, corresponds to this point, there's a gap, right? Pole 0 cancellation, and that's where something can pop up. Then we have 3 zeros that pull things down, and so you can see the effect of those 3 zeros there. Remember, they're not on the unit circle, so they're not pulling it all the way down. And the one that's in the middle has zeros on each side, so it's going to be the most effective. The 2 on each side that lie close to where there's the gap, those are only I guess I should be over here. Those are only slightly effective at pulling things down. And then up, there's the gap and it pops back up. So that's how we think about this. And again, we don't have to use this recursive view of this FIR filter, but it makes it easier to see why it behaves the way that it does. Much harder to figure it out using the explicit non-recursive FIR view of the transfer function. Okay, now let's generalize this to P echoes. So in the previous one, we had 3. Now we're going to have P echoes. So the A out in front keeps going in ascending powers. So we have, well, A to the 0, A to the 1, A to the 2, all the way out to A to the P. And each delay is an integer multiple of D. And again, we're going to keep the magnitude of A less than or equal to 1. Technically, nothing bad happens, but it's just less useful in the real world. So again, just doing our general transfer function. By inspection, we can go from this non-recursive difference equation to the transfer function just very easily by inspection. By this point, you should be able to do that quite easily. So we see that we have all these z's raised to powers of d. So again, we can do the finite geometric series and we get something that looks like that. So this looks just like what we had before, except before we had p equal to 3. So we got an a to the 4 and we got a 4 here, but everything else is the same otherwise. So we can go through the same deal here and find where our zeros are. Everything is the same except now p is general instead of being 3. And we can find where all the poles are. And we also see that the poles cancel the zeros just like before. And so we're left behind with PD zeros and PD poles at the origin. So here's what we have. So again, this structure looks like what we saw up here, except now we're saying not multiple of p plus 1. So k goes through all these numbers, but anytime it's an integer that's a multiple of p plus 1, we leave it out. And then here we have the PD poles at the origin. And so here is the idea of the spacing, except every pth one is missing. So remember back over here, when we looked at the pole zero diagram, where was that? Where I skipped it here. There we go. P was equal to 3, so we had 3 zeros in between where the canceling happened. Well, now we're going to have P, right? Because P was equal to 3 in this case. So we kind of know what to expect over here. So let's run z-plane. You can run this command where you set, prior to calling this, p equal to any integer that you want. And you can set the d to any value that you want. And so I've just made a few plots here. I'm going to go over them a little quickly. You can pause the video and take a closer look at this. But for p equal to 3, d equal to 8, that's the case that we had before. So we're seeing the 3 zeros in between the gaps made by the cancellation. Here's p equal to 4, d equal to 8. Still we see, or again, or slightly differently, we see 4 zeros in between the gaps. And I guess I should have said what A was for this, probably the same A that I used before. Now we've got P equal to 4, D equal to 9. And so again, it's the P that sets how many zeros there are in between the gaps. And then P equal to 4, D equal to 10. So really, the only difference between the D values is the spacing, right? So we can just see how closely spaced these are and how closely spaced these are. So if we look at P equal to 4, we've got 3 cases here, D equal to 8, 9, and 10. So we can look at the spacing gets narrower and narrower and narrower as D goes up. Okay, so we've got a pretty good handle on this particular comb filter. Still FIR. Now Orphanidis introduces the idea of an IIR comb filter. And we get there by taking the previous idea to an infinite extreme. So now instead of adding P echoes, we're going to add infinitely many echoes. So this is a nice, clever way to creep up from a simple FIR to an extended FIR and then take it to the simplest IIR form. And then we'll generalize this even further in subsequent notes and slides in this note set. So now ... So that goes on forever. So we have infinitely many terms, clearly an IIR filter, but not written out in an obvious recursive form. So what's the transfer function of this? So if we take the Z transform of both sides, and I should back up here. I still have this less than or equal to 1. Technically, we should avoid the equal to 1 because that will give us a marginally stable system. So now with an IIR filter, we have to worry about stability. And so we really shouldn't allow equality there. So I left it in the notes. I probably should have taken it out. Okay, now let's take the Z transform of both sides. So now we get something that looks like this. X of Z comes from this. Delay property gives us Z to the minus D times X of Z, and so on, and ... Now, if we factor out the X of Z and swing it to the other side, that gives us H of Z. And notice that we have this geometric progression, like we've seen before, but when we had only 3 delay terms, we could apply the finite form of the geometric series. That's always applicable. Now with the infinite form, we have to have this strict condition. A magnitude of A has to be strictly less than 1 in order for this to hold true. And if we do that, we get this form. And now we see, aha, that is the transfer function of an IIR filter. It has a very simple feedback structure. And there's no pole zero cancellation to make this end up being just all poles at the origin like we saw before. So, aha, an IIR filter. And we knew that was coming because that looks like it's got infinitely many terms in its impulse response. So let's walk our way through our little boxes here. We start with the transfer function now because that's how we got there. We didn't start with the right difference equation. We started with a transfer function that we got by sneaking up on that using the infinite form of the geometric series. So let's start there. We got this, and now we can multiply. We say, oh, here's our most negative power of Z, so multiply top and bottom by Z to the D, and we get this form. And now we can use that to find the pole zero diagram, but we'll get there in just a bit. So before we get to this, let's take this and by inspection, write it as the difference equation. From there, we can get the block diagram, right? Y of n, right here, is X of n going into the summer, plus a fedback delayed version of the output. So here's Y of n. It goes through a delay, so the signal here is Y of n minus D. So that gets fed back, multiplied by A, and added in to make Y of n. So yes, that is exactly what we have there. Now we can convert this into this form, find the zeros. Well, there will be D zeros at the origin, and then find the roots of this polynomial. So again, it'll be poles around this circle of radius rho, where rho is the dth root of A, just like we've seen before, except now it's just poles out there. Before we had zeros with some of them canceled and all the poles at the origin. Now we have all the zeros at the origin with a bunch of poles uniformly spaced around a circle of radius rho. So things have switched around a little bit. And then we can also get the impulse response. So we can go from this form, we can just do our standard, or even this form, depending on the table that you have. In my Signals and Systems course, we do inverse Z transforms on that form. So you can find this form, but we could also go back to our original view of the, with infinitely many terms in the output, and imagine putting a delta function in and get the result from that. So we get our delta, or our impulse response, and it looks like just like what we imagined it to be. Delta of n, a times delta of n delayed by d, and so forth and so forth. And that goes on for infinity. That's an IIR filter. And then we can look at what the frequency response looks like. So now we're going to have these very peaky, spiky things that go up. Whereas before, things were popping up because they were being blown up by the air hockey table through a gap. Well, now this pole is pushing things up. And depending on how close A is to 1, we'll set how close those poles are. Remember, that's the dth root. Rho is the dth root of A. But as A gets closer to 1, these will be closer to the unit circle. And these poles will give us more and more peaky, sharply peaked things at their locations. And their locations, we can see here, they're spaced by 2 pi d. So we've got 0, 2 pi d, 4 pi d, 6 pi d, and so on. And this particular plot goes out to 2 pi rather than starting at minus pi up to pi. Okay, so that's the idea. So this also looks like a comb. And that makes a lot of sense as well. Okay. And then in the DAFX book, they introduced something called the universal comb filter. And I put that in quotes. They didn't put that in quotes. I put it in quotes because this is really not the most general form of a comb filter. We'll look at that starting on the next slide, I believe. But this they call universal because it blends these two forms together. So we've got a feedback term, and we've got a feed forward term, and then we've got a term that kind of blends the two of those together. And so that's what, FB stands for feedback, FF stands for feed forward, and BL stands for blend. So we can get features of each of those two different types of comb filters. And this is coming in an audio book. So this is something that's pretty widely used in various effects. And we'll see this later on when we look at flangers and chorus and delay effects and echoes and things like that. And then they give you this nice little table that says how to set these 3 parameters. You can set them in different ways to get 4 different types of filters. And interestingly, we can get an all-pass filter out of this. So the comb filters, at least this universal comb filter, is related to the all-pass filter in a way. So that's kind of interesting in itself. But wait a minute, an all-pass filter is flat and a comb filter has these teeth? Yeah, that's kind of weird, but this is a mix of 2 different comb filters, and you can balance them just right so that they end up giving you something perfectly flat. Okay. Now, in Proakis and Monolakis' DSP book, they talk about a generalized view, the most general view of what a comb filter is. So I'm going to motivate that by going back and looking at our extended FIR filter that had 3 echoes. So the original plus 3 echoes. And let's take a look at that. Remember, that had a transfer function that looked like this. And so it had an impulse response that looked like that. So remember, we're going to have a 1, then a bunch of zeros. We'll have D minus 1 zeros in here. Then we'll hit an A. Then we'll have D minus 1 zeros. Then we'll hit an A squared, and so on and so on. So there's always D minus 1 zeros between those delta functions. So let's imagine starting with a different filter, which we'll call a prototype filter. And notice the difference. This one, the deltas were spaced every D samples with D minus 1 zeros in between. Now these delta functions are coming every sample. Other than that, the structure is the same, right? 1 and 1, A and A squared, and so on. Now, what was the transfer function of this thing? Well, again, that's easy, simple. Signals and systems, Z transform stuff right off your table and table pairs and time shift property, etc. Notice the difference between these two things. Z to the minus 1, Z to the minus D, Z to the minus 2, Z to the minus 2D, minus 3, minus 3D. That's the key that links these two things together. So the idea is we can start with any prototype filter that we want. I started with this 3-term simplistic FIR filter that links back to the extended FIR comb filter that we had. But in reality, I could start with anything here. How are these linked? Well, let's go back and remember our idea of expansion when we studied multi-rate. Remember, expansion was the preliminary step to increasing the sampling rate. Didn't really increase the sampling rate, but it stuffed in some zeros to kind of create holding positions for the ultimate correct samples that would be created through the image suppressing filter that follows the zero stuffing. So if none of that makes sense, go back and look at our very first note set on multi-rate DSP. So let's take our impulse response and expand it. So we're going to take this H tilde, that's our prototype impulse response, not of the comb filter, but the prototype that leads to the comb filter. We're going to expand it, and that was our symbology for expanding it. And what that means is stuff D minus 1 zeros between samples. So here we have a 1 followed by an A followed by an A squared. Here we're going to have a 1, and then there's D minus 1 zeros. And then we get an A. And then there's D minus 1 zeros, and we get an A squared. And then there's D minus 1 zeros, and we get an A cubed. So that's exactly what we've done. And also, if we recall our expansion result for the transfer function, the equivalent of stuffing zeros in the time domain was replacing Z by Z to the D. So that means everywhere there was a Z in our prototype filter's transfer function. So for this prototype, that was just a 1, A to the Z inverse, A squared Z to the minus 2, and so forth. Now every one of these Z's is going to get replaced by Z to the D, and now we get Z to the minus D, that was this thing, Z to the minus 2D, that's that with this substitution, and so on and so on. So we started with our prototype filter, and we, in the time domain, stuff zeros, or equivalently in the frequency domain, we replace Z by Z to the D, and we get our resulting comb filter. Nice. And that's the general way to make a comb filter from any prototype. Now, granted, it might not look like a comb filter. The ones we've looked at, the FIR filter, the IIR comb filter, those were the traditional classic comb filters because they looked like combs in the frequency response. Now we're going to say, let's abstract that idea. So the idea is we start with any prototype and we're going to combify it. That's a word that I just made up. So if we think about that replacing Z by Z to the D, we saw this back in our multi-rate study of expansion. Expansion of a frequency response means replace omega by D omega. So remember what that did. It scrunched in on the frequency axis. So if this is our prototype, and I'm just drawing it here for some other prototype frequency response, not the FIR filter that we were just considering on the previous page. So we're done with that. We're now looking at how we can take any prototype filter's frequency response and turn it into a comified version of that frequency response. So here it is. And yeah, I made this one with some teeth. And notice, really, we're looking at minus pi to pi. That's our regular. So this is some sort of, well, it's actually like an ideal differentiator is what it is if you've studied that kind of thing in a DSP class. But that's not important. We've just got this thing here. But if we look at it on a wider range, here I'm going out minus 2 pi to 2 pi. Now I can see some teeth there. What ends up happening? Well, when I comify this prototype to get my new general comb filter from that prototype, I have to scrunch it in. I have to scrunch it in by a factor of D. And so now if I take this and I scrunch it in by a factor of D equal to 5, this thing gets scrunched in by a factor of 5. So now this peak here, the top of the tooth that was at pi, is now at pi over 5. And this thing out here that was at 2 pi is now at 2 pi over 5. But remember, I was alluding in this picture to the fact that this just keeps on going, right? That's the periodicity of the DTFT. Frequency responses are periodic, 2 pi. So all of these things get squished in. So now if we're looking at minus pi to pi, I need to draw this correctly. There's our new minus pi to pi. Now I've got lots of teeth in here. I've comified this. Now, again, I will say it, this only looks like a comb if we start with something here that has some teeth that lie outside the minus pi to pi range. If this thing is just some sort of nice smooth thing, comifying it's not going to make a comb shaped thing, but we still call it a generalized comb filter. So the idea is we can take any prototype and comify it. And we can think of that comification consists of two equivalent ideas. We either upsample its impulse response, meaning we stuff D-1 zeros in between every existing samples, or equivalently in the transfer function, we take the Z and replace it by Z to the D. Either way, they both do the same thing. In fact, when you do one, you've done the other one. And that's how we go from some prototype filter to a comified version of that. So let's go back to our 3 echo extended FIR filter and see how we would apply this new idea to get from a prototype to this comb filter that we just started with. So our prototype was that. Now if I take this and comify it, so this part here gives me this frequency response, and then I comify it. So this goes to e to the minus j d omega. 2 omega goes to 2d. 3 omega goes to 3d. And I get this thing. Now, I can just put these things into freq z, or I can visualize it. I can say, okay, I know what that looks like. And notice that I've plotted this from minus pi to pi and actually gone a little bit farther out just so I can see the next tooth. And all of those get squished in to create a bunch of teeth between minus pi and pi. Again, this gives me teeth because I started with a prototype that had teeth. My prototype didn't have teeth. Everything will get squished in. I won't have a toothy comb filter when I'm done, but we'll still call it a generalized comb filter. Okay, so that's that. And then one final thing, looking at this from a block diagram point of view, we saw how we comify in the context of the impulse response, and we saw how we comify in the context of the transfer function, and we saw how we comify in the context of a frequency response. One last thing, how do we comify in the context of a block diagram? So if this is the block diagram of my prototype, I've just got all these delay boxes here, and I'm doing my feedbacks here with my A coefficients, and I'm doing my feed forwards with my B coefficients, so whatever they are. And here I'm showing that, we stop on the B side before we stop on the A side. That's typical. What do? Remember, Z gets replaced by Z to the D. So this is going to become Z to the minus D. This is going to become Z to the minus D. So each one of these things just gets converted into a Z to the minus D. But remember, Z to the minus D is really just a cascade of D Z to the minus 1s. So that might be a better way to think about it. We just insert here, instead of putting one delay, we put D delays in there. Or equivalently, we insert an additional D minus 1 delays in there. That's the idea of stuffing in the zeros. So it becomes pretty clear in this as well. Okay, so hopefully this gives you some perspective on this thing called a comb filter. Maybe you've seen it before, maybe you haven't, but we're going to use it a lot. This and the all-pass filter are going to be used a lot in subsequent units. We'll use the comb filters to find various types of like flangers and chorus effects that you may be familiar with applied to guitars and other instruments. And then we'll use comb filters and all-pass filters in the we'll use all-pass filters in phasers, another guitar effect that you might be familiar with, but we'll also use combs and all-pass to make reverb effects. So hopefully I'll see you in those later note sets.